So on 153, a teacher began testing or grading tests. The first 3 papers had a grade of 95%. So he concluded that the test was too easy. Is this a reasonable conclusion? Why or why not? And this is regarding sample size again. Okay. Even a class of 30, 3 is not enough, right? I'd say you should go at least quarter or a third. Okay. How about this? Write this down. A good sample size is between, I don't know, I would say actually more like 15% to 25% if you can. If it's greater than that, it's even better, right? But in general, rule of thumb, right, like 15 to 25% would be a good number there to have. Okay, not reasonable. Not a reasonable conclusion. Since he is basing it on a very small sample size. Grading 10 or more papers would allow him to make a more accurate conclusion. Something like that. And we don't know how big the class size is, but I don't know, university, if it's like a couple hundred students year one, right? Like it's even worse, like just to base it on 3, right? And it's not even random 3. It's not like it take like the first 3, right? If you took like random 3, maybe you're getting closer to, but even that is not, it's not good enough. Sample size is too small, end of discussion. Right? That's it. And here's one of those, you can guarantee to have something like this on a test, okay? A chart of some sort where a poll is taken, you have to make a prediction who's gonna win or how many votes somebody's expected to get, right? So what percentage of the student population was polled here? You get the total here. And this is 102 surveys that have been made. So this is basically an experiment, and you grab this many, you get 102. Out of 512 students, that's not bad. So 102 out of 512, let's get that as a percentage. We're going to times that by 100, and we get 1992%. A good sample size. Okay, let's make that observation that is a pretty good, that's why that they're asking you to do that. It's a pretty good sample size. Okay. If this poll is representative of the whole student population and all students are casting a vote, how many can NOAA expect? Okay, so prediction. We're gonna go probability of NOAA times larger sample. So probability of NOAA is 9 out of 102, and you're gonna multiply that by the larger sample, which is 512. And here it is, it says 45.17 votes, which is approximately 45 votes. Whole number. Page 153. Whole number only, okay? And the next one, I want to make this shorter because I want to get you to do a little bit of work yet. We're gonna switch this. How many votes can I expect it to separate? Let's cancel this one. Just put Noah in there. It'll make it a little bit easier. How many votes are expected to separate Noah from Zahara? Okay. So what we're gonna do here is predict probability of Zahara times larger sample. And so let's go back to the chart. There are 35 out of 102 respondents that said they would vote for her. And still the larger sample that we're predicting for is 512. And if you do that, you get 175.68, and that keeps going. So approximately 175 votes. The reason why I'm rounding down is because we don't quite have that extra vote to get you to the 176. So votes that can separate them, separation, all you do is you do subtraction there, right? And that is 130 votes. So Zahara would win by 130 votes. So that's the answer here. Notice that they didn't have Noah before, so technically you would have had to find how many votes for that candidate, and then how many votes for her, and then subtract. But I just didn't want to, it's too much work. So I just used my answer here. That's where the 45 came from. So maybe I will make an arrow here. Like that, so you know where the 45 comes from. Okay. All right. Moving on. So theoretical probability, it's not new to us. Like I've talked about it quite a bit. So we're just going to highlight a few things, and then we're going to jump into some examples here. So make sure you highlight theoretical probability or circle it. They're going to talk a little bit more about that. So in the previous section, you calculated probability based on data samples or trials, right? This is experimental. Okay. There's another type of probability calculation called theoretical. It is a probability that an event will occur based on the number of possible occurrences rather than the total number of items or trials. For example, if you toss a coin, there are two possible outcomes, landing on tails and heads, right? The theoretical probability, therefore, is 50% of landing heads, right? No news there. Compare this to the problem in the previous section, where you calculate the experimental probability of a coin landing on tails based on trials of 30. The answer was not 50%, right? 30 coin tosses was not 50%. And that is because theoretical and experimental may differ if the experimental sample size is smaller. Very important there. Underline that sentence right there is just to remind you. However, in a large sample size, experimental probability should be close to theoretical probability. And some of you need a bit of a, right, sample size. If you increase that, then the experimental probability should be approximately to the theoretical probability. Right? So that is actually true. You just have to have enough trials before you make your final conclusions. And I think I've repeated that enough times that some, like, you're probably saying, okay, I got it already, Mr. Dixon, don't keep talking about it, right? But for some of you, it was a long, long weekend, right? So it doesn't hurt. Okay, so I'm going to ask you to quickly answer these questions. What's the probability of this, this, and this? Just write down as a fraction underneath each one of them. Just a little practice there before I assign more. Write down a number. Don't just wait for me. Probability of drawing a heart. There are 13 hearts out of 52. You can actually reduce that. It's 1 out of 4. Drawing a blackjack, right? The probability here, there are 2 of them, right? Because there are 4 jacks, half of them are black, so 2 out of 52, which is 1 out of 26. A card other than a diamond, let's do this, D with a line on top, 52, and this 52 minus the 13 diamonds, right? That's 39 out of 52, which is 3/4. Think about it, if a quarter of them are diamonds, then 3/4 would not be diamonds. Oh, you can't see that, sorry. There. And the reason why it's blank down here is because they had lots of, they kind of had the solution, how they came up with that down there. So I just got rid of that. Okay. Just don't ignore this, like the B and the C, right? We've done that just now. Don't worry about that. I'm going to skip a few questions. And I'm going to ask you to try question 2 on 156 real quick before I explain the second part there. And I just realized I need to erase stuff here. So don't worry about what is written there. On 156, try question 2 on your own. So just question 2, okay, on 156. Good. Right. So the probability of rolling a 5 obviously is 1 in 6. Even number, it'd be 2, 4, 6, right? With a 6-sided, there are 3 options, so probability of even is 3 out of 6, which is 1/2. So probability of odd would be the same, right? Multiple of 3. A multiple of 3 means like if you take 3 and you go up by 3 to get your next number, the next one will be 9. So in this case, probability of multiple of 3, it's 2 out of 6 options, right? Which is 1 in 3. So that's how you would do that. How about this here? A number less than 3. What would be the probability of drawing a number less than 3? Yeah. 2 out of 6. I get creative with the number. The 6-sided die is too boring already, so all my quizzes and stuff, expect all kinds of weird things happening there. Less than 3, so there's only 1 and 2, right? So it's 2 out of 6, which is 1/3. 2 outcomes out of 6 possible. Question 3, 12-sided die has faces 1 to 12. Of course, if the die is tossed, what's the probability of landing on an odd number? Right? Odd would be 1, 3, 5, 7, 9, 11, right? So probability of odd, there's 12 outcomes, and it's 1, 2, 3, 4, 5, 6, which is 1/2, right? That would be odd. A multiple of 2, so you start with 2, and then it's 2, 4, 6, basically even, right? And 12. Don't forget 12 because it's part of the outcomes. M2, I'm going to call this. So there's 6 out of 12, which is still 1/2, or 50%. How about this? A number less than 7. What would be the probability of getting a number less than 7? Six out of 12. You're correct. So it's 1/2. Why is it always half? It's always half, maybe, right? Watch out. What if it says equal to or less than 7? Then 7 would have been included here, so it'd be 7 out of 12. Right? All right. This next example is where things change a little bit. Okay, so I'm going to ask you to write down a header. Where are we at? 11:30? Yeah, we can do a couple here. Dependent, we're going to write down dependent. Make sure write this down. Dependent events. Okay. I would box that in, and I would highlight that. If you have a highlighter or a marker or something, make sure it stands out as you're flipping through your notes, because this is where things get a little trickier. Let me see here. I'm off by a page. Can we get a 158 here? 158, this is where dependent event starts. So write this again. Dependent events under that spinner, okay? Sorry, this is on 158. And I will say this, on the side here somewhere, I will say that dependent events, I'll put an arrow out. First event affects the second event. Okay, make sure you write that down. Keyword you want to look for, no replacement. Okay. If something is being drawn and not put back, you're affecting the outcome of the second event. Okay. So that's what dependent events, that's how that changes now. So the first event affects the second event, and the keywords you want to be looking for is no replacement or not put back or something like that. It's not always going to read the same, but it's going to give you a clear indication of what's happening from one event to the other. Okay? So Louise is playing a card game. She draws one card from a standard deck of playing cards without replacing the card. There's a keyword there. And then draws a second card. So draws one card. This is going to be the first event. The first action, right? And then this is the second event. Drawing the second card. Okay? What is the probability that the first card drawn is an ace? So we're going to do that right next to it here. Probability of an ace, there are 4 out of 52. Okay? We're not going to reduce that. We're just going to leave it like that for now. Now, this is where the dependent event comes in. If the first card is an ace, if the first card actually happens to be an ace, what is the probability that the second card is a 2? Okay. So we go probability of drawing a 2. What happens to the total number of cards now? You used to have 52, right? 52 cards. You take one card there, so that's -1, right? That means that there's 51 cards left. And that's what you put down here. So you put 51 cards. So now your probability of drawing a 2 is out of 51. So that has to be established. That has been affected. And then you have to ask yourself, is the fact that you drew an ace, is it going to affect the total number of 2s that are left? No, right? Because the ace is not a 2. So that means that you still have 4 cards that are 2s. Right? 4 2s left, right? Total down by 1. Okay, so that is just left like that. I'm going to add a C here. If first card, I'm going to summarize it, card was an ace, what's the probability of second card being an ace? Can you please write that down? So if the first card was an ace, determine the probability of the second card being an ace as well. It's the second action here, right? First event happened, now you're asking a probability. So probability of grabbing an ace again, 51, because total number of cards is now down. And how many aces are left if the first one is ace? 3, right? Right? Some of you are whispering it and some of you are showing. So yeah, 3. So it's 3, right? 3 aces left. 51 cards left. Right? So this is how dependent events, if the first event affects the second one. If you replace it, right? If you put that card back in the mix, it's always back to what we used to do up until now. But if the card is not being replaced, you got to watch out for that, because then the total will for sure be affected. The top number, not necessarily. The top number is only affected if the first event actually brought down the number of aces in this case, right? And so you have to watch out for that. One more thing, and then and that'll be it for today, and then we'll do more tomorrow on this stuff. I have a worksheet that goes over this in more detail. 159, probabilities involving the letters in a word. So quite often you'll be given a word, and then the idea is that you cut it up and you put all the letters in a bag, and then you're going to draw from it, right? So consider the word Mississippi. It's a very popular one. If the letters making up the word would be placed in a bag, and one would randomly select a letter, determine the probability of drawing an I. So first of all, let's add up the letters. You got to make sure you understand this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do you count the same? Please confirm. Because it's Monday. Is it 11? Yeah, okay. So we're out of 11, and how many I's do we have? 1, 2, 3, 4. So that's it. We're just going to leave it at that. Probability of drawing a P. We have 2 P's there. Probably a vowel. You know what a vowel is? A, E, I, O, U. You remember that, right? I hope. Okay. So there's 1, 2, 3, 4. Basically all the I's. So not, all of these assume that you're putting them back after every draw, right? Now this, if Biff draws a letter S, first event, and then without replacing, draws another, right? It's the second event. Explain about what the probability would be now. The probability of the second letter being an M. So in this case, you know you're down to 10, right? You no longer have 11 because you drew one, didn't put it back, right? And you drew an S at first, so the M's, how many M's are left? There's still one left, okay? Only 10 remain, okay? The probability of the second letter being a P, probability of P, it's out of 10 now, Since the first event does not affect the number of P's I have, it's still 2 out of 10 or 1 out of 5. Okay. The probability of the second letter being another S, you're down to 10 still, and since one S has been already taken off, we have 3 left, right? 10 remain. Only 3 S's left. Right, so it'll be 3 out of 10. And one more thing, before you pack, remember when I made you write down dependent events? We're gonna have to scratch that. My bad. I'm truly sorry about that. 156. You know what how you can fix this is if you can fit an IN in front of it. It's independent event. And I'm gonna talk more about that tomorrow. So on page 156, it's independent events, not dependence. Thanks.